In this chapter, we're going to learn the basic approach and the nodal analysis, mesh analysis, and we can see we also learn the superposition theorem, the source transformation, Savani and Norton equivalent circuits, and this one we don't learn this one. And we can see from the contents, nodal, mesh, superposition, source transformation, and Savani and Norton equivalent circuit. All of these we have learned it in the DC circuit analysis, right? So now we're going to see how to use those theorems, these methods, in the AC circuit analysis. After this lesson, I hope everyone can explain how nodal and mesh analysis can be applied to the AC circuit, and explain how superposition theorem, how source transformation can be applied to AC circuit analysis, and also explain the key characteristic of Savani and Norton equivalent circuit. Right. That's the thing. That's all the things for this course, for this lesson. Okay? Right. The first section is basic approach. The basic approach means how to analyze the circuit step by step. Right. The first step, okay, if a circuit is DC circuit, we don't have the circuit analysis. We don't have the first step, because the first step is asking you to transform the circuit to the phasor or frequency domain. How to translate it? You still remember? Right? We say we have R, L, C, the basic circuit elements, right? And in the time domain I use T, right? And for frequency domain, we have angular frequency, so I use omega. The R in the time domain is R. The R in the frequency domain is still R. Right. Now, you should know we're talking about admittance. Okay? Impedance. Okay? And we also have admittance, right?
Okay.
Right. For admittance, it also belongs to the frequency domain, right? So, for admittance, we have G, right? G for conductance.
Yes, admittance.
Right.
Subtractance
And
plus
L is the inductance. In the time domain, we use L. In the frequency domain, if we use impedance, we use omega L. We add one omega here. And for admittance, we use omega L over 1.
or 1 over x.
Do we have minus here? Okay. And for capacitor, we have
1 over
minus
omega c.
omega C over 1. Right?
If you without considering
Because we don't have the J inside, right? We don't have the J inside. If we have J inside, it should be J omega L, okay? If we have J inside, it should be J omega L minus J here, minus J here. Clear? And for this one, it should be J
omega c.
I recommend you guys, remember this one, right? Because they are
Disproportional.
no, not really proportional. This
Disproportional.
one reciprocal of this one reciprocal as well.
I mean disproportional.
Yeah? Reciprocal of the impedance. Admittance is a reciprocal of the impedance. Okay? impedance. Then you can write out the admittance directly. Clear?
Yes.
Right. Right. So for all of us, if we get an AC circuit, the first step for us is to transfer the circuit to the phasor domain or the frequency domain. That is the same, okay? The phasor domain is also the frequency domain. It has two names for one thing, okay? Then, the second step, we are trying to solve the problem using the circuit techniques in the DC circuit. Because after the transformation, the circuit is transferred to a circuit with complex coefficients. Okay, with complex coefficients. Then we can use all the skill we learned in the DC circuit and apply it to the AC circuit directly. Okay. You can use nodal analysis. You still remember the shortcut? Right? You remember the shortcut? Okay. Because for all of yours, after you graduate, basically, it is seldom for you guys to solve a circuit like this, because this one is small circuit, right? Right. So maybe after 3 years and after 6 years, you see a circuit suddenly, and then maybe you forget something, right? But you make sure you remember the KCL, KVL, right? And you should know the basic circuit analysis method, and the best way is to remember the shortcut, because the shortcut is the most easy way to write out the circuit equations in a shortcut. Okay. Then the last step, we transform the result phasor to the time domain, because after this way, the solution we get is in the phasor form, right? It doesn't have the angular frequency inside. It just has the amplitude and the phasor angle, the phase angle. And we still need to transfer it to the time domain, okay? Of course, the phasor is a thing, a mathematics thing we used to analysis. It doesn't mean we really do something to the circuit. We didn't change anything, right? We just use another analysis method. So after we solve it, we still need to transfer it back to the time domain, okay? So we know the frequency domain is the scale we use to analysis. Okay, in the practice, we just have time domain, right?
Yeah.
Okay, now we're going to see the next content, the nodal analysis. Do you still remember the topology? Do you still remember the topology? What is the nodal? Still remember? If you don't remember, you can feedback to your book. You can go back to your book and see what is the nodal mean. Okay. Right. We know for nodal analysis, we can see this example and see how nodal analysis works. The basic nodal set analysis, we are using the KCL law. In our last course, we say the KCL law and the KVL law can be applied to AC circuit directly. It is sigma I dot equals to 0, right? And sigma U dot equals to 0 as well. Is it? Remember? Right. In the time domain, we don't have the dot. In the frequency domain, we have one dot here. Okay. And we're trying to use the nodal analysis to find Ix. You still remember how to do the nodal analysis? What is the first step? Select a reference node, right?
Okay.
Select a reference node
It's already
and
selected.
V1, V2, V3. Well,
two nodes.
you can choose
One, two,
anything.
yeah.
Okay.
Okay.
You can choose anything. Right, let me have a look. How does it work? For this circuit, we see we have a dependent source inside, right? And we also have anything different? No, just this one. So now the first step, we will transfer this one to what? To phasor circuit, right? So try. And fix it here, and you know how to transfer it, right? Just have a try. Draw a figure. Transfer this one to the phasor circuit. And now there is one thing we should notice. That is the phase angle, right?
Yes.
We don't have the initial phase angle,
Zero.
so we can suppose one. Clear? We can suppose the initial phase angle of the source is 0. Clear? Just suppose one. If we don't have the phase angle, just suppose. It is more like the reference, right? We select the reference node, and all the potential is regarding to the reference, right? But the potential difference is always the same. But the potential is decided by the reference node. Now it's really happy because all the guys are trying to do the practice. You know? If you guys just stand here and do nothing, I will be really angry. But you are trying to make practice, so I'm happy. Finish and check. And put the value inside. Put the value of circuit diagrams inside. Put the value inside. Then put here. We put 10 ohms here. And for this one is L. So we put J omega L inside. Put J omega L here. For those other things. Okay. Put the phasor value inside the figure, okay? Finish. Just wait for them. For this example, now it should be 20 angle zero. And J omega L is J omega is 4, right? Or J. Is it? What is our omega?
4.
Yeah. Right. And is omega. Omega is this one. Not that omega. Okay. Not this omega. This omega. The small omega, not the big omega. Okay, this one is small omega. This one is big omega. Check it out very. Are you sure? J omega L. Okay, use this one. Point 1 is C. J omega C. C is point 1. So you cannot use equal here. No, you cannot use equal here. Yeah. It's all like that. Okay. J omega J. J is still J. No, if you put the minus here, the J should be in the denominator. Minus J. J is here, not yeah. Omega C. Or what is omega? 4. Just put 4 inside. Minus 0.1. Minus 0.1. So the value should be yeah. And then this one, yeah. Okay. Okay, everyone. Hello, everyone. Look at the blackboard. I put value of all the value interfaces. So you can see, right, I forgot to bring my point here. I forgot to bring my point today. So what can I use today? Okay, so for this one, we know the amplitude is 20, and the angle, the initial phase angle is 0. So it should be 20 angle 0, right? And for R, you know, in the time domain it's R, in the frequency domain it's still R. So it's 10. We don't change it. But we can see the thing we change is the source, the C, and the L. For other, we don't change it. So we don't need to calculate the R, we just need to calculate the J omega L and minus J, 1 over J omega C. Okay. Right. For the L, you can see we have 1 Henry and 0.5 Henry here. So for 1 Henry, we have J omega L, and we can see our omega here is 4. So put the 4 inside and put the L equal 1 inside, so we get 4J. And for the 0.5, for the proportional, we know it must be half of the 1 Henry. So it should be 2J. And then we're going to see the capacitor, the 0.1. We know it should be in this form. So we put minus J and omega and the C. We know the omega is 4, right? C is 0.1. So we know omega 0.1 equal to 0.4. 0.4 means 2/5. So the value is 2.5. And then we get this one. And from the value we can see the minus thing is always capacitor, right? The positive thing is always inductive. And we also need to know it is impedance. Okay. Right. After we calculate the value, we can transform the circuit into the frequency domain. The figure should be like this. And we know now the 2Ix in the original figure is 2 small ix. But in the new figure, it will be 2 big Ix or I dot x. Okay, in the slides, they use the big I to stand for the phasor. But okay, I don't know in your book if it is I dot or something. It is I dot or
No.
it is the big one, okay? But in the Chinese book, we always use the I dot. And we put a dot. We put a dot on the coefficient because sometimes if we put a dot there, we know it must be in phasor, right? But if we don't put it inside, sometimes it will be confused, right? And we can see after transformation, all the signal in the circuit are transferred to the phasor. So here the controller of the dependent source is transferred to phasor as well. So the value changed from small ix to big Ix. Clear? The big Ix is here. For nodal analysis, we know the first step is always to choose the reference node. We can see the reference node is selected here. And now we are going to select the V1 and V2 to select the nodal voltage. Here we can see the first nodal is here, the second nodal is here. So we put V1 here and V2 here. And then we can write out the KCL equation. Clear? Write out the KCL equation using the nodal voltage. Clear? Right. Then we know now this point is nodal 1 and this point is nodal 2. And we're trying to write out the KCL at nodal 1 first. Right. Help yourself. Write out the KCL for nodal 1 and write out the KCL for nodal 2 and write out one more equation for what? For the dependent source. Clear?
Yes.
Still remember?
The Ix equal V1 over
Okay, have a try. Guys, have a try. You have 2 minutes to finish this one. I just give you 2 minutes.
2 minutes.
Yes, 2 minutes. Because it's really easy, right? Just treat it like a complex resistor, okay? Treat this one like complex resistor. Okay, ignore this one. Just think it's all resistor, okay? Just the value difference, okay? And then it is a pure resistance circuit. It's really easy, okay?
Yeah.
Right? You can use the KCL and you also can use the shortcut way. But for this example, I don't recommend you guys to use shortcut because we have dependent source inside.
Yes.
If you have dependent source, you can write out the equation, but you
Is
still
it a
need to
bit-
transfer it back to the
Main equation.
algebra equation and solve it out. So I don't recommend you guys to use the shortcut way here. Okay, we use the traditional node voltage analysis method. Do you have any long bar and I can use one? Long bar? to I2 plus I3, right? And you just need to calculate the I1 and I2 and I3. Okay, so for I1, we know it is the current goes through this branch, right? And we already know the voltage at this point, right? It's 20, right? It's 20, angle 0, right? So the value should be 20 minus V1, or 20 angle 1, angle 0. Okay, 20 angle 0 minus 1. Okay, right? And then for I2, we know I2 is the current inside here, inside this branch. So it should be the voltage difference V1 minus V2. Because now we suppose the direction of the current is here, right? So it's V1 minus V2. If we change the direction from here to here, it should be V2 minus V1, okay? So the value should be the voltage difference over the resistance, okay? So it should be V1 minus V2 over J4. Then go to this branch. We say the voltage difference is V1 and V0. We know V0 is 0, right? So it should be V1 over the resistance. Okay, the complex resistance, okay? Right, this one is for the V1 analysis, and you can see here. Right. Here, he didn't put the angle inside Y. And we know the angle means, what does angle mean? Angle means cosine theta
Yes,
plus
suppose 0 equal
sine theta, right? If the angle theta is 0, it becomes cosine 0 and sine 0. Is it? So sine 0 equal to 0. So this one, this part eliminated. And cosine 0 is 1. So we know the angle 0 means 1. Okay, remember? So the next time when we see the angle 0, we can just ignore it because it's equal to 1. Clear? Right? So we get equation which has variable V1 and V2. And then we are going to analysis the V2. For node V2, we can see here the V2, right? The V2 should be the current go inside V2 equal to the current go outside the 2. And here we have 2 big Ix. Is it? So now we calculate the I1. I1 equal to what? See, I1 is V1 minus V2. V1 minus V2 over 4J. Is it? So what is I2? I2 should be V2 minus V0. Is it V2 minus V0 over what? Over 2J. And then 2Ix is still 2Ix. Then we get this equation. And we can see we get V1, V2, and Ix as the variable. So 2 equations, 3 variable. We still need one more equation, one more extended equation for Ix. How to find out Ix? And we can see here, the Ix is the I passing through the minus 2.5J. So we can write out the VCR equation for the C. Okay, so we know VCR equation is U equal to IR, right? So our U here is minus v0, right? And v0 is 0. So it's equal to v1 equal to ix 2ix, right? Oh no, sorry, ix times minus 2.5j, is it? So now we get three equations and we get three variables, and we can solve out the solution, a unique solution, right? Right, after the calculation, we know we can solve out it, and you can solve it at home. And here, when you put this one, put the value of ix back into this equation, the equation now changed to two equations with these two variables v1 and v2. And this equation area is in the algebra form. And we can transfer this one to the matrix form by take out the coefficient of v1 and v2. Okay, take out the coefficient v1, v2, v1, v2, and put the v1, v2 as a vector. And the right hand side is what? Is the value of the source. Okay, so now we get a form of, what is that? Something equal to,
This equation make a matrix form.
yeah, this one is matrix form. This one is voltage v1 and v2. Okay, it doesn't have any meaning. Okay, it doesn't have any special meaning. Just solve it. Solve it by computer, by MATLAB, or by Kramer rule. You can use any method. Still recommend Kramer rule. v1, Kramer rule, v1 is equal to delta 1 over delta.
Yes.
Delta is the determinant, right?
Yes.
Delta 1 means replacing the I column by the B. Clear? By the B, and calculate out the determinant. Then you get the V1. And for V2, we got the delta 2 over delta. Okay, so it's easy, and you can solve it out at home. You can see in the denominator, it's the determinant of this one, right? And in the denominator, we replace the first column by the B. Then calculate out the determinant. And for V2, we replace the second column by the B, and then calculate the value. But here we should notice, when you do this calculation, the value should be in a complex number, and you need to transfer the complex number to the polar, okay, to the polar coordinate.
Yes.
This one is not the polar, this one is a complex.
Yes.
And we need to transfer this complex number to the
polar.
polar coordinate, like this. And then we get the amplitude and the angle. How to transfer it? You know, for complex number, a plus bj, right? So the amplitude should be a square plus b square and square root. Is it? And the angle is arc tangent b over a. Clear? So we use those two equations and we get the amplitude and the phase. Okay. If you don't remember, go back to the PPT of last course. Right. And then, after we get V1 and V2, and we can get our Ix as well. And then we know we get the value of Ix, but this one we still in the what type of form? In the polar coordinate, right? and we still need to transfer the phasor to the time domain. And we know the phase angle still the same, the amplitude still the same. The only difference is the angular frequency, right? And we know all the standard time domain is in the cosine form. For the international standard, we use the cosine. For Chinese standard, we use the sine. So, when you work in China, when you see sine, you know it is the Chinese standard. When you see the cosine, it's international standard. I told you guys this because you study in China, and you might work in China, so you must know the difference, okay?
Yeah.
Right, now we're going to see the second example. For this example, it's really easy one, right? Easier than the last one. The only difference is we have two sources inside. One is the voltage source, and another one is current source, another one is voltage source. So here, you can see there were phase difference between two sources. This one is 0, and this one is 45 degrees. So, now I think this circuit has been transferred to the phase to the frequency domain. So we don't need to repeat the step 1. We just need to solve this one. Okay, come on. Solve it by yourself. Select the reference node here and node 1 and node 2. For this example, I ask you guys to use shortcut because we don't have dependent source inside. So I ask you guys to use shortcut. Okay.
Our last example, this book answer is wrong. Yes, ma'am. That's why I was confused for 5 minutes. For this I use find x and y. I use this one like p1 and p2. X equals ed minus b epx and ad minus bc, and for y equals as minus ec and ad minus bc. So
because the calculation, we don't care. I told you guys, I don't care about calculation. I just want you guys to know the thinking process. Okay, I don't care about the result because result is computer's work. It's not our work. Okay? Right? Right? Trying to solve this one, use the shortcut way. And we know, hello guys, look at the blackboard. For shortcut way, we know, now our variable is v1 and v2, right? So we can write out the equation like this one. So it's v here, v on the left hand side, so this one is g. On the right hand side should be the current source value, for current source.
So we need conductance.
You must know it's generally b equal to I. So now we need to calculate the inductor. But I'm not sure. I think the figure is for impedance, not for inductance. So we need to transfer this one because you can see how to judge this one in impedance or in the impedance.
1 over minus 3 is
Because for C, okay, if the C is minus, it must be in impedance. Okay, so we know the value here is in impedance. Okay, but here we calculate the G. So we need to use admittance.
here. So this
So
value
we
is
need to
3
take the value of this one, take the reciprocal. Remember?
Yes.
Take the reciprocal of this value.
0 or 3.
Forget the blackboard. Now we're going to calculate the matrix of G, right? To calculate the inductive matrix. But actually, here we doesn't call it inductive matrix anymore. How to put this one? How to put this one? Do you still remember?
Yes, ma'am.
The equation in the mathematics is in GVI, right? But in the frequency domain, we change it to y. Remember? We change to y. So now we're going to calculate the y11, y12, y21, and y22. Clear? And now, if you confused, don't worry. Just use G and then change G to Y. That's the thing, you know. That's the thing. Okay, for Y or for G, we know the G is the conductor connected to this one, to the node 1. And we can see for node 1 here, how many resistance is connected to it. We just have 4 ohm, right?
2 ohm.
So its conductor should be 1 over 4. And we still has another one, a capacitor. So we should have 3J over 1 minus 3J over 1. But here we see we change the minus J to J. So we have J times 1 over 3. This one is for Y11. For Y22, we are going to see node 2. For the node 2, we have 1 over 12 because we have 12 resistance connected to node 2.
Yeah.
And we have another 4 ohm. And we have 6 J ohm, right? So we put 6 J ohm to the denominator. Then we see we get the Y11 and Y22. Those two things are called self what?
Impedance. No. Admittance.
Yes. Self-admittance. Okay? Self-admittance. And then we also have mutual admittance.
Yes.
For mutual admittance, we are going to see the circuit elements connected between node 1 and node 2. What's that?
4 on over 4.
It's 4. So it's minus 1 over 4.
Yes.
Right? It's minus 1 over 4. Because the neutral one is negative. Clear?
Yeah.
Then we calculate out the y11, y22, y12, and y21 because y12 is equal to y21. So we calculate this one and we get this one. And then we solve this matrix. Then we are going to see this one. We know the current go inside is positive. So for node 1, the value should be 3, but we still have something go inside from there.
Yeah.
So it should be what?
That's number 2.5.
This source transformation. Trying to take this part as source transformation. We know
2.5 2.5 I equal 2.5 B1 to B2 is 2.5.
yeah, it's 2.5 minus 2 point plus, sorry, plus is plus 2.5 and go for 5 degree, right? And for node 2, and we say it's obviously minus 0.5 angle 45, right? Now we still need to remember for this part, its current source go inside, but this one is not current source, it's a voltage source. So we need to do source transformation, right? To transfer this source to current source. But you should know this one is companion with this one. If it's not companion with something, you cannot do this, okay? Okay, for this example, they are using the supernode analysis. They're taking this one as a supernode, and they applied the KCL law to supernode directly. But we know why I didn't use the supernode here, because for supernode, we cannot use the shortcut way. So, actually, if we have the computer, the shortcut way is the most easy way. The supernode is not. The supernode is a one-way to analysis. We should know, but actually we don't use it too much in the practical. Okay, we should know this. Right? For the KCL to the supernode of this one, we know the current go inside is equal to the current go outside. So, the current go inside is 3, right? The current go outside should be here, the voltage difference V1 minus V0 over this one. And for this one, V2 minus V0 over this one. And for this one, V2 minus V0 over this one. So we get this. For this one, we have 3 unknowns, but 1 equation. So we still need to get some more equations. Sorry, two variables, sorry. We need to apply something to the supernode. For the supernode, we know, go back here, for the supernode, we know this one is the voltage source, right? So that means we know the voltage difference between V1 and V2. So one more equation is V1 equal to V1 minus V2 equal to 10 and go 45 degrees. Clear? Right? So now we have 2 equations and 2 variables, and we can solve it out and get the value. But here we need to notice this one and this one is in the polar or coordinate. You should use your calculator to calculate it out. Here. You should use your calculator to calculate it out. Right. Now we are going to see the mesh analysis. For mesh analysis, we're going to see the example 1. Right, we know for mesh analysis, we use the KVL. KVL means sigma u equal to zero, right? So we need to find out the mesh current. We use the mesh current and write out a KVL equation. The mesh current is our variable. We must know this, okay? The mesh current is our variable. And now we're going to see this circuit. Now this circuit has been transferred to the phasor circuit, to the phasor frequency domain, right? Then we don't need to make the circuit transformation anymore, right? It has been transformed. So we start from step 2, right? If we want to use the mesh analysis, we write out the mesh current firstly, right? For this one, we have 3 mesh. So we put this one, mesh 1 here, and mesh 2 here, and mesh 3 here. And this one is a very, very easy way, right? Because we don't have the dependent source inside. Hi guys, please try shortcut way to solve it. Do you remember the shortcut way? If you don't remember, you want to take a picture? It's quite late. Just take this. Okay. If you want to take a picture next time, in more costume. You cannot wait, because I just have a very, very small blackboard, you know? It's really small. So, now we know, now our variable is I1, I2, and I3. Clear? And now when we know we need to get something in this one. Here we need to calculate the matrix, right? So we know for the BC, this one is I. For the BC is RI equal to B. We know this. But for the AC, it should be B. I equal to B. So now we're going to try to solve B11, B22, B33. And B12, B13, B21, B31, B32, B23. Clear? And then for this part we know is V. It's voltage source. Rise. And I put the arrow there, and you know it's rise. Okay, voltage source rise. Right. Now, what is the V11?
8 minus 2.
V is for the impedance, right?
Yes.
For V11, we're going to see the
8 minus 2 is there.
To the loop 1, right? For loop 1, we have 8O
minus Z2.
plus J10
Yeah.
minus 2J. Clear?
Yes.
For V22, we are going to see the loop 2, right?
Minus
It's
Z10.
equal to
Oh,
minus 2J minus 2J
2Z.
plus 4, right? Finish.
Yeah.
And for these 3, we get this loop, right?
Yeah.
We just have 1, 2, right?
Yeah.
So it should be 10J minus 2J. Is it?
Yeah.
Right? Then we're going to see the mutual impedance. 2, 1. We see 1 is here, 2 is here. So we focus on here, right? So it should be 2j because it's negative, right?
Yeah.
So our b 1, 2, sorry, 2 is b 1, 2, b 2, 1 equal to 2j as well. Clear?
Clear.
Then we're going to see b1, 3. What is b1, 3? We're going to see
Minus
this
10J.
one and this one. So it should be minus 10j. Clear?
Yeah.
So b3, 1 is minus 10j. So how do you feel about this? I put something on the blackboard. Is it better?
Good.
Is it better?
Yeah.
Okay. Right. Then we still know here is going to be the same, right? So we need to find out something between 2 and 3. 2 is here, 3 is here. So it's 2j as well. B3, 2 is 2j and B2, 3 is 2j. Then we know we calculate out this matrix. Then we are going to see this vector. For loop 1, no source, so it's 0. Is it? There is no source here, right? For loop 2, the voltage rise is minus 20 angle 90 degrees. Is it? The problem is this one. How to write out this one?
Because this side I3, so
How to write out this one?
for this line we can write 10j minus 2j plus 5 angle 0. This one I3.
I3 is equal to 5 angle 0.
Yeah.
But here we should write out the B.
I mean 10j. Now it is our matrix. Yeah? For this situation you can write for I3. So it's minus 10j, 2j, 10j minus 2j plus 5 angle 0. It's coming this way. It's positive. Because my current is fine with positive. Current, loop and current is same direction. So if I put it left side, it's positive.
They cannot be like this. I forget how to do this, but sorry, I'm going to see the PPT. It should be in chapter 3, right? Do I talk about the shortcut here? It's not clear. Why? It's not clear. It's GB, we're going to see not GB, we're going to see the branch current nodal analysis. Nodal analysis. Mesh analysis. Cycles supernova. Shortcut. Should we do one says one? No. Sigma IS times R in 1. I don't put any time here. It's good. This is our voltage source.
For this problem, if we use
Oh, I see. And supposedly, I remember. And supposedly here, right? What is the very now we're going to see here. For this type of problem, we need to suppose a V here. Suppose the V for this one. Suppose this one should be a voltage source with voltage V. Okay, so now this one should be this one positive, this one negative. Sorry, this one positive, this one negative. So it is rise. So it's positive V. It's positive V. Then we need to get one more equation for this thing. Clear? Not clear. Actually, you're not clear, right? Okay, now the problem is, we know, now we're going to find out a voltage source rise value. But here it's a current source, it's not a voltage source. So we need to suppose this one to be a voltage source because of a theory, I forgot the name of this theory. It should be, in Chinese, we call it substitute theorem. Substitute theorem. That means for one element, it should be, okay, for one element, if we take out this node and this node, right? We can calculate R input, right? If all the outer circuit is fixed, the voltage and the current on this port should be fixed. So we can put any current source or any voltage source to here. We can think this one is a current source with a fixed current or a voltage source with a fixed voltage. Clear? So here we can use a V, a voltage source, to replace this one. Just we're going to know the value of the V, and then we're going to calculate out this V. Clear? Because now we can see we have 1, 2, 3, 4 unknowns, but we just have 3 equations. Where is the third equation? The third equation is I3 equal to 5 and go here. It's really easy. But now we see this equation seems strange, right? It seems strange, but we still can solve it. How to solve this? We need to transfer this matrix form back to the algebra form. Still remember algebra form? Transfer this equation back to the algebra form. Then substitute I3 inside. And then you will get 3 equations with 3 unknowns. But these 3 unknowns is I1, I2, and V. It's not I3 anymore. Okay? So if we have something like this, we must know we need to replace this one by a voltage source V, and then get this equation with the variable V, and then introduce this one inside to change the variable from I1, I2, I3 to I1, I2, V. Then solve it out. Clear? Okay. Right. This is the shortcut way for this, and now we're going to see the mesh analysis for this example.
This is the minus V or just V?
It's V because it's voltage rise.
Yeah, but this side you write this V,
Yes,
so it's minus V.
No.
No,
This one is current source, so this point, this one is positive, this one is negative. Rise. Follow the arrow, it's rise.
No, I mean you have both equations of V. You write V, this side is V, and also is write this left side is also V.
Which side? No, it's still V. You can change the value. You can change the algebra equation will be changed. Okay?
I understand that.
Then you still have here, and just put negative inside and it will change. You know? You don't need to care about minus b or b. I just want to see b. We don't want minus. Okay? Just put a negative here. You just put a negative for both sides and you change the sign. Okay? Okay. Now we're going to see the mesh analysis of this example. We have my mesh 1 and mesh 2 and mesh 3. The traditional way, if we want to analyze the mesh 1, we use the sigma u equal to 0, right? Right. For sigma u, we know it's I1 times 8, I1 times 10j, I1 times minus 2j equal to 0. Clear? And for the mesh 2, we have I2 times I2 minus ij times minus 2j, I2 minus I3 times 2j, and I2 times 4 equal to minus 20,
Yes.
angle 90 degree.
Yes.
And you also can put this one
Let's say.
to the left hand side, it will become positive. Okay? And for the loop 3, we have I3 times 10j, and then we see this one. But here we can see we just use KVL to mesh 3, but we already know the I3. So I just put the I3 to 5 angle 0 inside, and we get this. And you can see, if we have some current source inside, if we still want to use the shortcut way, it's okay, but it seems more difficult, right? And we can use the traditional KVL analysis. It might be better. But sometimes, you know, with this circuit, we just have 3 loops. But if you have 300, you know, if you have 300, I think it still might be better.
Yes.
You know, it still might be better. Because, you know, for this one, we can put it into a big matrix like I1, I2, I3, and V. You know, we can get an expanded matrix with I1, I2, I3, and V. We can get this type of equation, and then we use MATLAB to solve it. It's more quick. Clear? So, in practice, we always choose the way we can get the equation quick to solve this problem. Because in the practical, the dimension of the circuit is not 1, 2, 3. We have large dimension, okay? We might have maybe 10 loops, 100 loops for a very, very big power grid. So, for that type of circuit, we cannot just maybe use one or 3 equations to solve. We have a large equation. So, for that time, we don't think it's still a good way to do the traditional analysis. Okay? Right. This is the way to use the grammar rule to solve the solution, and you can try this at home. Okay? Right. Now we're going to see the mesh analysis example 2. See? Look at this. Right. It seems complicated, right? Why I say this one is complicated? Because it has 1, 2, 3, 4. Okay, it has 4 mesh. Try to solve it. Okay, try to solve it. Can we use the shortcut way? If we use the shortcut way, we see we have what? We have 1 and 2 current sources inside, and we are supposed to be 1 and 2. It's more complicated. So it is better to use the traditional way.
Yeah, and on super mesh here. Logic.
Yeah. If you use the super node, it's okay. If you use
Super
the
mesh.
super node, it's okay. Okay. If you use the super node, then you need to suppose the I here. If you use the super node, you need to suppose I here. So I still think it's better to use the traditional way, but
So,
here, for this
super mesh.
example, it is the super mesh. It is the super mesh. If we use the super mesh, we still get one here. Still a problem. We still get one here, and here. So I don't think it's bad. It's best way because we still get one here. Try to solve it by the traditional method. KCL. Don't use the super mesh. You can use the super mesh actually. Take those two as the super mesh. This one is really easy. Do you still want to talk about this one? If we don't use the super mesh, it's okay. But it's still better to use because the 4 ampere is on the a joint branch, so it is better to use the super node. Super mesh. Otherwise, we cannot just write out the equation directly. We also can write the 4 ampere equal to I4 minus I3. It's the same. It's the same actually. It's one more equation, right?
Yeah.
If we go back to the equation itself, we know one equation, one variable, right?
Yes.
If we get 5 equations,
5 variables.
5 variable, 5 group, we can solve 5 group variable. 5, okay, now see this example and try to solve it. It's a little bit more complicated case. Take the mesh 3 and mesh 4 as the super mesh.
Yeah.
You know how to solve super mesh? And you can use the shortcut way as well. But for shortcut way, because here we know we have 2 current sources. So if we use shortcut, we can solve it. But for the right hand side, after we list the shortcut equation, we still need to do more work because we know our V1 and V2. I still think the shortcut way is a good way because you can see for the shortcut way we can just draw out this one and suppose V1 and V2 and we have one more equation and 2 more equations and we can solve it out by MATLAB.
Need 2V. Need new 2V.
Yeah? And 2V, 2 more equation, right?
Yeah.
This one with it's easy. Just add 2 more equations inside. But this equation seems strange because it has 5 variable inside. And the 2 more equation seems has no relevance with V1 and V2.
For me, like the traditional way is good.
I know. Because you don't have a computer with you now.
My computer is here, but
I know this this one is simple. This one is a simple circuit. If you have 300, suppose you can see
Here will in shortcut.
it will be a large work.
I think more than 6 loops, so we need to use a shortcut.
I can try to write it out. I use the shortcut. You use the traditional way, okay?
Okay.
Everyone? Okay. I see. One, four, two, three, 0, 2, 4, 3, 4, 0. I1, I2, I3, I4, V2, V1, V10, V2, minus V1, V3, minus V2, V2. It becomes an equation like this one. Then 2 more equation, I2 is minus 3, I4 minus I3, will become like this. 6 strings, right?
Oh.
You can see here. Compare this one. Compare this one. Compare this one. And compare this one. But actually, you cannot think like this. You can see here. This one, this one, this one, this one. The same as this one. Right? The same like this one. Just add 2 here. There's another color. Just those 2 are new. Right? But you can see here, those 2 are those equations. Right? Clear? So we just change the dimension of the matrix. It's still easy. So I think we still don't like the short cover, right? But it's still easy, you know. You can see, if we times this one and this one, still this equation. If we times this one and this one, still this equation. Right? Still this equation. Times this one and this one, still this equation. Times this one and this one, still this equation. Actually nothing changed. Just add 2 more equations inside. The matrix will become a large dimension matrix. Clear? But we still can solve it out by mathematical way. Right? Okay. And if you want to know this method, just go back on page 1. Because I might make some mathematical mistake here, but the idea is clear, right? The idea is clear. Just use matrix product, okay? This one times this one times this one, and get the value, okay? Clear? It's clear. Right. Okay, now we are going to see the result of the example 2. For this example, because the 4 ampere is a joint branch of mesh 3 and mesh 4. Hello, look at the blackboard. Okay. For this example, the 4 ampere is a joint branch of mesh 3 and mesh 4. For this type of element, we can say this loop is a super mesh. So now we just write out 3 equations, one for super mesh, one for node 1, and one for loop 1 and one for loop 2. Okay, for loop 1, we say it's where is minus? Oh, okay, minus 10 is for this one. It's 8 is I1 minus I3. I1 minus I3 times 8 plus I1 minus I2 times minus 2j and minus 10 equal to 0. This one is for this loop. And for mesh 2, and we can see here, the I2 minus I1 times minus 2j plus I2 minus I4 times 5j. Sorry, for mesh 2 we don't need to calculate it because we have current source here.
Yes,
so I2 equals to minus 3
3.
left. Okay, for the super mesh, we're going to see here. Okay, we can start from here. Okay, so it should be I3 minus I1 times 8. Then we go here. Is I3 times minus j, right? Then we go here.
I4.
Right. It's I4 times 6. Then we go here. For
I4
this
minus
element,
I2.
we have I4 minus I2 times 5j. Then we finish this loop. We get this equation. But actually, this equation, they're not in the way I was talking, right? For me, I just use the actual current go through the element times resistance. The actual current goes through 8 is I3 minus Ij, right? Right? Is it? And for the 5J, the actual current goes through it is I4 minus I2. Okay, so you must know this, and then you can get the result. Then we say we have strip mesh, so it has one more equation for this one. For this one, we know the current goes through the 5 ampere is I4 minus I3 equal to 4. I4 minus I3 equal to 4. Right. Then, if we simplify those three equations, actually it's 4, right? 1, 2, 3, 4. Simplify those 4 equations, and we get 2 equations. And then we can use MATLAB to solve it. Because they can be transferred into the matrix form, and you can use a calculator, and you can use MATLAB to solve out the result. And you also can use a Clever rule to get the result. Is it easy? Actually, if we think all the component is resistor, it seems easy, right? You don't treat it like inductor. You don't treat it like capacitor. You just think this one is resistor, okay? Resistor with complex number, okay? With complex number coefficients, then everything will be easy because it becomes a pure resistance circuit, and we use all the scale of the DC circuit directly to AC circuit analysis. Okay, clear? Right. Then we're going to see the superposition theorem. For superposition theorem, we know if a circuit has source operating at different frequencies, actually it's not a general case, because in the general case, for example, for our power grid, normally we have all the frequency in the same angular frequency, okay? But these conditions still exist. Well, for example, if we want to export our energy to another country, if our neighbor country has 60 hertz and we use the 50 hertz, then the angular frequency will be not the same. Okay, for this type of analysis, we know we should use the superposition. Okay?
But you need to change your frequency level.
Yes, we actually need to change the angular frequency to the same in practical. Okay, but here you just say if we have, it's just a case. Just tells you if you have some sources in a circuit, but they don't have the same frequency. What should we do? Okay, when a circuit has sources operating at different frequencies, we will solve the different phases circuit for each different frequency and obtain individual time domain responses. What does this mean? We need to draw 2 different figures, right?
Yes.
2 different figures.
2 different.
Because every element has responses to every individual sources. Okay? The total response is the sum of all the individual time domain responses. That means we can have some sub-figures. For every time domain, we have a subplot. For every frequency we have a frequency domain figure. For example, if we have 3 frequency domain figure, but when we transfer it back to time domain, we just have 1. Clear? find out the I0. I0 is here, and using the superposition theorem for this circuit. Look at the circuit. These circuits are in the same frequency, angular frequency. So it's not in that case, but we still can use the superposition, right? We can treat this one work individual and treat this one work individual, and then calculate the superposition signal. Okay, right? For I0, we can use it like I0 dash and I02 dash. It's not dash. It's prime. It's prime. Prime and 2 prime. I prime is due to the voltage source. This one. That means we enable this one. How to enable this one? Set it to 0. Okay? Set it to 0. If a current source is set to 0, that means this one is break. Clear? This branch is break.
Ma'am, this line please again. You say this one will break. Please reason.
If we set the current to 0, I equal to 0 means it's break.
Oh,
you don't need to write it down.
No,
okay.
I think maybe you say something like
this is being right. Right. And here, I02 prime is due to the current source, means this one. This one will come along, and we need to enable the voltage source. If we enable voltage source, just set it to be 0. If our V equals to 0, means this branch is short connected.
Yes.
Clear? Okay. Then we can draw 2 figures. One figure like this, and we have the voltage source walk along. And one figure like this.
Yeah.
We have the current source walk along, and we can get our I02 prime.
Yeah.
Okay, go back to the first one. Now we need to get I0 prime, and we enable our current source now, and we get this figure. Clear?
Yeah.
For this figure, we just have one source, and all the other things are in the complex resistance. All the others are impedance. Clear? All the other elements are in impedance. Okay. Then we're going to solve the I0. How to solve the I0? And we can calculate the V spanning, right? Can we calculate the total spanning impedance? Can you calculate spanning impedance?
Yes.
It's easy, right?
Yes.
This one and this one in series. If they're in series, it's plus, right? So it's 8 plus 10, right? And for this branch, it's 4 in series is minus 2j.
Yeah.
So it's 4 minus 2j. Clear? And then this one
And this one parallel.
in parallel with minus 2j. And we get this one. Let me have a look. Right. Okay, so in his example, he just take those parts after V.
Yeah.
Yeah, they take those parts after V. So they get those two in series, then in parallel with this one, and they calculate it out. And then they think those two parts are in series with V, and then they use the VCR, the Ohm's law of impedance to calculate out the I0. It's more easy, right?
Yes, but when in PPT we write it Z20. Is Z2. I not equal Z20 over 4 minus.
Why? Because this one is V equal to VI. It's V equal to VI. Z is here, I is here. V equal to VI. Here is VCR, it's Ohm's law. In the time domain, our Ohm's law is V equal to IR. In the frequency domain, is slope here, we get the V, the voltage, equal to the current times the impedance, the total impedance. Then we can calculate out our I0.
And for G, what is
Which one?
4 and 2?
Which one?
First one. For G,
For G.
yeah.
Then minus.
What is G? Oh, it means for G.
Yeah.
It should be GV. It's not G actually, it's YV. It's YV equal to I.
And to get I0 prime.
I0 prime, yeah?
And next one, G minus J2 parallel 8 plus J10.
Yeah.
What is,
Just
where
look
is
at
4 and minus J2?
no. Look at this part.
Yeah.
This part will become V. This part will become V. And then 1, 2, V in series. This one and this one and okay. Can we have them? Sorry. This part, just sort this part to be a V. Okay? So 1, 2, V in series.
Yes.
You can take this one as R1, R2, R3. Clear? R1, R2, R3. And you calculate the total R. But now it's V1, V2, and V3. You calculate the total V. Total impedance V. Okay, clear? Then we get the I0. And this one, you can write it in the complex form like this one. And you also can write it into the phasor coordinate. But now we don't transfer it to the phasor coordinate. Okay? The polar coordinate, sorry. Because we need to get our I0 to prime first. Then we're going to get our I20 prime. For this one, we say we have a current source inside, so we are trying to use the KVL law. Right, we get loop 1 and loop 2 and loop 3. And we know for loop 3, you can write I3 equal to 5 directly. And we just need to write out the KVL equation for I1 and I2. For I1, we know it's I1 times 8 plus I1 minus I3 times 10G and times I1 minus I2 times minus 2J into 0. This is for the loop 1. For the loop 2, we start from here, okay? It should be I2 minus I3 times minus 2J. Then we go here, it's I2 times 4, right? And then go here, and go here, right? So it should be 2I2 minus I1 times minus 2J equal to 0. Then we get two equations, one for loop 1, one for loop 2, another for loop 3, I3 equal to 5. Then, 3 equations to solve I1, I2, I3 variables, and we can get the value. We can get a unique solution. I1 and I2 and I3 2 prime. Right. Actually, sorry, we get I1 and I2 and I3. It's not I2 prime. Our I2 prime is actually minus I2.
Yes.
So, we catch the value of I2, we get the value of I0 2 prime. Clear? Then our total I0 is equal to the first figure plus the second figure. Clear? The I0 1 prime plus the I0 2 prime because of the superposition theorem. Then we can plus this one and this one to get a complex number. And then transfer this complex number to the polar coordinate. And we get the phasor form. We get the phasor form like this. Clear? You can use the calculator. It's up to you. Then we finish this example. Now we're going to see the example 2. Hi boys. For this class, all the skill we have learned. So we are trying to when you go back home, we need to finish all the calculation of the class. In our class, I just show you the thinking process, okay? Show you the equations. But I didn't tell you how to solve it, right? When you go back home, you need to make practice to solve it, okay? Right. Now we're going to see the example 2 of superposition. Calculate V0 for the circuit using the superposition theorem. What is that? And we can see we have one voltage source, and one current source. And this current source is in a combination. Is alone, right? It's in a joint branch. So for your mind, we know if we try to solve it, we might need to use super mesh, right? But here we use the superposition. We need to draw 3 figures, right? Clear? Okay. If this one walk along, clear? If this one walk along, we need enables this one and this one. If we enable current source, it's break. If we enable a voltage source, it's short. Then no, it's not like this. It's not. It's this figure, right? It's this figure because this one open, this one short, and then for this one. If this one walk along, we need enables the first one and the third one. This one and this one, they are all voltage source. So we use a wire to instead of them, right? Then we get where's the figure? Let's have a look. Where is this one? Front V1, 10 cosine. Yeah, become this one. It's become this figure, right?
Yeah.
It become this figure. We use 2 wires to instead of those 2 voltage sources. And then we need the third figure. If we want to make this 5 volts operate alone, we need to enable those 2. So this one short, this one open, and then we get this figure. Okay, so now we're going to see the first case when the 5 volts walk along. If it's walk along, we know this one is open and this one is short, and we get this figure. This one is a really, really simple one, right? Just resistance and 5.
Yeah.
So we use Ohm's law, and we get the value of V1. How to get the value of V1? We use voltage divider, right? The 1 over the sum times 5. Clear? Right. But here, one more thing we should notice is the sign of the V1 is opposite to 5B. So value calculated is V1 is minus 1. Clear?
What is this plus 1?
Then we are going to see if the first source walk along. And we transfer this one to the frequency domain as well. And you can see here, this one, amplitude 10, phase angle 0, right? And this one, and this one, and this one, we just use the J omega L and minus J1 over omega C, and we get the value, okay? So we don't repeat this thing again, okay? But you need to know if you want to calculate AC signal, you need to transfer the figure to the frequency domain here. Okay. Right. Right, if we change this one to here, we know if this one walk along, this one open, this one short, and the figure become like this. Please look at this one. We know we need to calculate the impedance, right? When we calculate the impedance, and we calculate the current, and then we can calculate the V. Clear? Let me have a look. I think they might calculate those parts first, right? Yeah. They calculate those parts. The minus 5J are in parallel with 4, so they are product of the sum. Clear? The product of the sum, and we get the value of this impedance. It's really equal to this one. Then we use the voltage divider. The impedance of this one is 1 ohm. 1 ohm over the sum. Now the sum should be 4J, 1J, and those parts V. So it's 1 over 1 plus 4J plus V times the source, 10 angle 0. And then we can solve out our V2 and transfer this into the polar coordinate. Then we can transfer this back to the time domain. Because our omega, we already know, omega is 2, right? So it's amplitude cosine omega 2 t minus the phase angle. Clear? Okay. Then for the third one, we need to find out the 2 sine by t. If this one walk along, short this one and short this one. Okay? If this one short, we get this one. If this one short, we get 4 ohm. And we transfer all the elements to the phase domain, and we get this figure. Okay, now look at this one. It's still a pure impedance circuit, right? For this pure impedance circuit, now we're going to see what? See the voltage on the 1 ohm. Okay, so we're trying to solve this one.
Well, there is a 2 sin 5t. They are transferred to 2 cos.
Because this one is sine 5t, we need to transfer this to cosine. We need the minus 90 degree. Okay, we need minus 90 degree. If we transfer cosine to sine, we need plus 90 degree. So it's different. In Chinese, the student always transfer cosine to sine. For international, the student always transfer sine to cosine. So sometimes I was confused as well, you know.
Ma'am, I can transfer this voltage, this goes to sine, and I can put my current is also sine. I can send this voltage sine to cos to sine.
Omega is not the same. It doesn't matter because they are in two different figures. We don't have omega inside. We don't have omega in this figure. This figure is for omega equal to 5. You must know this. And this figure for omega equal to 2 is different. Okay?
Yeah.
It's different. Omega to 2, this figure, omega equal to 2, this figure, omega equal to 5. Okay? And then we're going to solve it out. Now, look at here, for this part, those two are in parallel, so the product of the sum, and we get V1. And then, let me have a look. It's equal to 10J, okay, here. I1, V1, 10J. Okay, then 1, 2, 3, those two are in series. In series means just simply plus V1 plus this one. Okay, right here. I1 in parallel, in series with this one, so it should be 1 plus V1. Okay, and here, suppose this one 10J, and this one, we can use the current divider. Here, the current divider is the opposite impedance over the sum. Opposite impedance over the sum. So it's 10J over 10J plus 1 plus V1 and times the current source. Current divider, okay? And then for this one, we can calculate our D. Okay? Let me have a look. We can calculate our I1. Our I1, if we want to get our V1, we use the Ohm's law, V equal to IR. Clear? And our R here is 1 ohm, so we get our V3 directly here. And now the V3 is in the phasor form, is in the polar coordinate. So we need to transfer this one to the time domain. But here we should notice the omega is not 2 anymore.
Yes.
It's 5. So that means for the original circuit, we have 2 different sources in different frequency angle. Okay, so we draw different phase domain figure for different
Omega.
frequency.
Yes. Our one voltage omega is 2
Right.
and another is 5. So we have 2 different voltages.
Right. Then we get our V3. And for this, we transfer this one to the sine. Why? We don't need to transfer it to sine actually. And our V0 equal to V1, V2, V3, and we just simply plot all of them and we get a result. And here, if you don't change it, it's okay. Clear? Okay, now we're going to see the section source transformation. That means how to transfer a current source to a voltage source and how to transfer a voltage source to a current source. They are accompanied with some impedance. If they are accompanied with some impedance. Okay, let me have a look. This one is a typical
Having
circuit model. This one is typical circuit model with the voltage source and impedance Vs. So our Vs is equal to Vs times Is. If we calculate the V and I for the port A and B, you will get the relation. Vs equal to Vs times Is, and this one and this one are equivalent because this one and this one has the same port equation with the same value. So for this figure, we have Is equal to Vs over ds. If we want to transfer this one to this one, our Is is equal to Vs over ds. If we want to transfer this figure to this figure, Vs, you notice the Vs is always the same, but the source value is different. The new source value should satisfy, actually this is Ohm's law, right? The new source value should satisfy the Ohm's law. And the voltage source is always in series with Vs. And the current source is always in parallel with Vs. That's the typical model. Okay, so this relation is for the typical model. If you change the connection, those two equations are not satisfied anymore. Those two equations are just for those two models. Okay, for this topology, okay? Okay, now we're using the source transformation to solve some circuit. Please look at the example 1. Do you want a break? Okay, 5 minutes break. I'm tired, so. I have to go back home. I have to go back home later. Because I forgot to bring my mobile with me, so I don't have money.
Oh.
I don't have money with me. I don't have money to eat. Oh, I have some money. Okay, I don't need to go back home. Okay, have a break. So the happy with today is confusing because we always use the DC circuit analysis scales for AC. But they're similar, right? They're really similar but different concepts. We change the resistance, we change the resistance to impedance, right? Resistance becomes impedance, and conductance become admittance, just like that. Other things are the same. Ohm's law is the same, everything is the same. The response when the source goes wrong. That means you are one source, I am one. Okay? So you will bring in a response for me. I will bring in a response for the next one. The total response is your response for the next one. Yeah? But when you work when both of us work wrong, you know? Okay, so what type of source is it? So the power source means I, right? If we enable it, we let it equal to 0. If I equal 0, means what? It's not connected. Yeah. Okay. And we put the value of U here inside, and we can get our IS into this one. Then, let's have a look. Well, where is our V1? V1, can you have a look? Where is our V1? 3, 4, 3, 4, 8 plus J. Where is 8? 8. 4J is here. 4J is here. 3 is here. This one and this one. The product of the sum is those parts, right? Product of the sum, right? So this part is our V1, right? Why we calculate V1? V1 is equal to 0.5 plus J. Okay, right. Now he's doing a transformation to simplify this circuit. For those parts, it is calculated out as V1. Our V1 is equal to 0.5 plus J, 1.5 ohm. So it should become a resistance, not resistance, it becomes a impedance of V1 in series with IS, right? And we can transfer it back to the voltage source. Okay, if we can transfer this one back to voltage source, we keep the V1 the same, right? Just the connection method changed to series. In series with the voltage source, and the voltage source value should be IS times this one, right? I as times E1, we get this one. And then we know this one is simplified to a voltage source, and other things are all in series, right? Other things are all in series. And then we put the Vx equal to, this one is V. Why is Vx? Okay, it's voltage divider, because now we're going to calculate the Vx, right? So it should be the value of this impedance over the sum and times the source voltage, and then we get the Vx. For this Vx, it's in the complex form, and we need to transfer this into the phasor form, right? It's like this. And we also need to transfer it back to the time domain after the calculation. Please make sure of this. Then we're going to a new section, Savani and Norton equivalent circuit. For this one,
I'm looking, man.
okay. For this one, it's also easy because we know the Savani and Norton equivalent circuit, and we need to calculate the Norton voltage, and we need to calculate the Norton.
Time. Doesn't feel.
Actually, Norton current, sorry. We need to calculate the Savani voltage and Savani resistance, and we also need to calculate the Norton resistance and the Norton
Time.
current. Okay, do you still remember the way to calculate it out?
Yes, ma'am.
And we say the Savani voltage is the open circuit voltage of the port here,
Here.
and the Savani equivalent resistance is, do you still remember the
Thevenin
four
resistance.
ways to calculate the Savani resistance? The
Yes,
four
ma'am.
ways?
Yes. Out.
The first way, we need to turn off the independent source
Yes.
and then calculate resistance.
Yes.
The other way, short, sorry,
Cancel.
open short method, right?
Yes.
Do we need to enable independent source? We enable the independent and use the open short. We use the open circuit voltage over the short
Circuit.
current,
Yes.
and we get the Savani equivalent. Then the 3 and the 4, we also need to enable the independent and apply the alter
Current or
current
not?
source or
Voltage
voltage source,
Yes.
and then take the derivative, not derivative, take the u over I, and we get the value
Yes.
of RTH.
And another is outer resistance.
Okay, and the last method we need to calculate, we can add outer resistance, but that method we don't recommend.
Yes.
So just ignore that one. So those are the methods to calculate our Savani resistance and Savani voltage. Now we say all the scale we can use in the AC analysis directly. Please look at this figure. We can see this one is the model, right? But now our model is not resistance anymore. It's the impedance Savani. Impedance Savani. And we can see if we use the impedance Savani instead of the R, they are the same. Because our formula is still in the Ohm's law. Okay? Our formula is still in the Ohm's law. We just change the RTH to VTH. And we also know our RTH equal to Rn, so they are changed to VTH and Vn as well. Those two are equivalent. We must know this, okay? Those two are equivalent. And this one satisfies this relation. Okay, our VTH equal to V Norton times IN. Or you can put it VTH because they are equivalent. So that's the same, okay? Now we're going to see the example because the formula we already learned. Okay, so we're going to see the example. Please find the Savannah equivalent at terminals A and B. That means A, where's A? A is here, E and here. So out of this port is a black box like this. Okay. So now we want to find out the equivalent circuit for the black box. Okay, so now from this port we look in. We want to find out our VTH. If we want to find the VTH, we need to set the voltage source at 0 because for this one it's really simple. We don't have dependent source inside. So we just set it to 0 and then calculate the equivalent impedance. If we set this to 0, a voltage source set to 0, we use a wired instead of it, right? We use a wired instead of it. Then this part becomes this, and this part becomes this. And then what is the value of VTH? And we can see from this port 1, 2, 3, 4, they are in parallel, then in series, right?
Yes.
Okay, right. So if this one and this one in parallel, it should be product of the sum, right? If this one and this one in parallel, it will be product of the sum, right? And then they are in series, just simply plus this one and this one. And we get the Savannah impedance, VTH. Clear? And now this one is in the complex form, please note. And then we need to find out VTH. Okay, here I need to point out, you can calculate the RTH first, and you also can calculate the VTH first. It's up to you. But I recommend you guys to calculate the VTH first. Okay, calculate VTH first. Right. If you want to find the VTH is the open circuit voltage. Clear? Yes, now we want to find out the open circuit voltage of VAB. Now our VAB is our VTH. Okay, look at this circuit. Now this circuit is in the phase domain, right? It's in the phase domain. Right. If we want to calculate the VTH, what should we do? Can we see it directly? No. We can't, right? But we know the VTH is the voltage on this one, and also the voltage on this one and this one, right? So we can calculate the voltage on this one and this one, or on this one and this one, and simply plug that. Can we? Okay. So, right. It looks they calculate those part, right? So they calculate I1 and I2. Right. What is the value of I1? It's equal to, right, what, let me have a look. What do they use? Right, it's very easy, right? It's voltage, it's voltage divider or current divider?
Current divider, man.
No.
It's two current.
No, actually it's voltage divider. You can see here, it's voltage divider.
But they find this current.
You can find out, calculate the current. The current goes through is this one over this one. This one over this one is the current. Actually, it's not I1. This current inside here, right? Is it? You can see if we write out KVL for this, right? For this loop, write out KVL. Can we? Write out KVL for this one. So it should be this one. So it's strange, right? I1 should be here. You can see I1 should be current inside here. Is it? Yes, because of the KVL. So it's strange. 8 minus it's strange. I think it is better to draw a loop current here. But put the loop current I1 here, loop current I2 here. The I1
I2
should be, no, it can't be like this. It cannot be like this. It cannot be like this.
because this
Just take the KVL. Take the KVL of this loop. It will be those over the sum of this one. So we get I1, right? Sorry, it's not like this. Sorry, my mistake. Sorry, my mistake. It is the current divided.
Yes, ma'am.
It's current divided. Because this one is one branch, this one is one branch. So, it's strange. Why is like this? Okay, we just suppose we just suppose on this branch current is I1, so I1 times this is equal to the voltage, and I2 times those is this voltage. So we get this one and this one, and then let me have a look. After we get I1 and I2, B, C, D, A, B. Where is B? B, C,
D,
D, E, A,
B,
B.
yeah,
Oh, for this loop.
yeah.
For this loop, we can write out the KVL equation. Our VTH should be the voltage on here and the voltage on here, and then we get VTH. Sorry, I made a mistake here. Oh, sorry. Here, we just use the current that goes through here is the KVL actually. The voltage on here is equal to the voltage on here. Clear? Not clear. Okay. I1 times the resistance on this branch is equal to this. We use the KVL for this. KVL. The voltage here equal to the voltage here. The voltage here equal to the voltage here. Voltage here equal to the voltage here, we get this one. Voltage here equal to the voltage here, we get this one. Clear? Okay.
Like
and then we put the KVL equation for this loop, and we get this equation, and we solve it. Okay. Then, right. Okay. This one is for Norton. Find out I0, where's I0? Use the Norton theorem. Okay, this one is a little bit more complicated. So firstly, we need to find the Norton equivalent at terminals A and B. Now A and B is like this one, and we remove this part and calculate the equivalent. And we enable independent source, means open current, short voltage. Short voltage here, open current here, and the equivalent circuit become like this. And now you can see those parts are short by this wire. So the Vn is equal to 5 ohm. Then we are going to calculate the In, the Nodal current. Okay, I think they short the circuit, and then the circuit become like this, and they use circuit analysis and calculate out the In. They use the direct way, just short it. Because for In, we are going to calculate the short circuit current. Okay, short circuit current. So we just short this one and calculate the current In. Okay. Right. For this one, we know this one they use the they use the sugar mesh. Did they use sugar mesh? Mesh 1, sugar mesh, yes, they use sugar mesh. Okay, original circuit we have 3 mesh, but here we have a current source on the joint branch. So we take I2 and I3 as the sugar mesh. So actually we just need to write out 2 KCL equation for mesh 1 and sugar mesh. For mesh 1, we have I1, okay, we ignore this one, start from here. I1 minus I2 times 8 minus 3J, because they are on the same branch, okay? Yeah. I1 minus I2 times 8 minus 2J. And then we go to here. It's equal to I1 times I2, I3 times 10 plus 4J, because those two are on the same branch. And then go here is equal to
minus is equal to 40J.
40J. Okay. Then this one is for this. And then we go to this super mesh. We can start from here, okay? If we start from here, it should be I2 minus I1 times 8 minus 2J. And then we go here, it's I2 times 5. And then go here, go here, right? It's I3 minus I1 times 10 minus 4J, right? And then we go back. We finish this loop, and we get this equation. But we know here we have I1, I2, I3 variable, but we just have 2 equations. So we add one more equation for the super mesh.
Yes.
We go back here, we see for the node A, the current go in is equal to the current go out. So I2 plus 3 equal to I3, right? Then we get this equation. So we get 3 equations for 3 unknowns. We can get a unique solution. Clear? Okay. And when we solve out this equation, we get In in complex form, and we can transfer this one into what type of form? We can transfer this into phasor form as well, right? Right. And we get our Vn, and I get our In, and our circuit will become like this one. But our purpose of this circuit is asking us to calculate the I0, so we need to use the current divider as well. Okay, current divider, the current goes through this one is equal to the opposite impedance over the sum and times the source, right? Opposite over the sum times the impedance. Clear? And then we get the value in complex form, and then we remember transfer it to phasor form, then transfer to time domain. Okay, don't forget this. Okay? Right. That is all for today, because for OP amplifiers, we don't want to talk about this part. Okay? So this part is I think this part you enjoy. DP
Hmm?
is an analog circuit teacher.
Online.
Online.
That time.
So
Yes,
you already
okay.
finished?
But
The
I
analog
yes,
circuit, you already finished?
last semester.
Okay, so just for one semester.
Yes.
That was for one semester. Mine was for 2 semesters. Okay, that's all.
But this semester we did the digital circuit.
Okay, now we're going to see the summary of today. We applied nodal and mesh analysis to AC circuit. And actually, we know all the DC skills can be applied to AC circuit analysis. We just change resistance to what? To impedance, right?
Yeah.
And we keep all the things the same. And we add one more step before analysis. We do the domain transformation. We transfer the time domain to frequency domain, and we still need to remember to transfer it back. If a circuit has 2 different frequency components, don't forget we need to draw 2 different figures. Make sure, okay? This is very, very, very important. Okay? If we have 2 different frequency signal inputs, we need to draw 2 figures. If we have small, draw 3. Okay? If we just have 1, we can just draw 1 figure. 1 frequency, 1 figure. Because frequency domain is for 1 frequency. It's not for all frequency. Okay? But time domain is for all frequency. Okay? Right? And the concept of source transformation can be applied in the frequency domain. Just need to remember one thing. Transfer the resistance to impedance and use the Ohm's law for AC circuit, okay? For AC circuit, we have U equal to VI. For time, for DC circuit, we have U equal to IR. Okay, just remember, it's still Ohm's law, but different condition. Okay? Right. That's all today. See you next week. Okay, see you next week. I hope you're happy today. I hope you can learn something, okay?
Of course, ma'am.
Okay, please.
Now to go.
Put the value of I and I. You want to calculate this one.
অবশ্যই